This call is now being recorded.
Okay, so now the recording has started. So the chapter number 2 and 3 here in your textbook deals with a detailed discussion on the conduction. So we have already discussed what is conduction in your chapter number 1, that is the basic of heat transfer. We have discussed the basic laws of heat transfer. In this we will be discussing the one-dimensional and steady state conduction. State conduction. So if you see the PPT here, share the PPT now. So all of you are able to see PPT.
Yes, sir.
Yes, sir.
Okay. So let's move to the chapter now. So we have already discussed what is conduction in our chapter number 1. So heat conduction is defined as the transfer of thermal energy from the more energetic particles of a medium to the adjacent less energetic ones. So conduction can take place in liquids or gases as well as solids, provided that there is no bulk motion. So if there is a bulk motion, in that case there would be a convection mechanism of heat transfer. In that case, and if there is no bulk motion, then only we have to consider the conduction. So if you take an example of any body, okay, and if you point out that what is the amount of the heat transfer taking place from this, then you can have a particular value or a magnitude of it. Now if you want to specify at what particular point what is the value of the temperature, so that point you need to specify first what is that point's location. So if you consider that there is an example that there is a hot baked potato, and you need to know what is the temperature at a particular point, you need to know first what is the location of that point. Also, we need to also have an idea about the direction of the heat transfer, whether the heat transfer is into the system or it is leaving out the system, plus what is the magnitude at a particular point. So although the heat transfer and temperature are closely related, they are of different nature. So unlike temperature, this heat transfer has a direction as well as magnitude. You can see for temperature in this example also, the temperature at a particular point you can just tell the magnitude of it. There is no particular direction associated with the temperature. But if you talk about the heat transfer, there is a magnitude also related with it. Along with that, a direction, whether it is entering into the system or leaving out of the system. Now, to define the heat transfer at a particular point, you need to have an idea about the magnitude as well as the direction. So, therefore, we must specify both direction and magnitude in order to describe the heat transfer completely at a point. So, if we take an example of a simple plain wall, and we say one side is at some temperature, isothermally be maintained at some say 18 degrees centigrade. But if you are taking some body and you say at a particular point its temperature is somewhat 50 degrees centigrade, and then you have to determine what is the magnitude of the heat transfer. So you need to have an idea about the temperature distribution of the body, and you also need to have an idea what is the direction of the heat transfer. So what is the magnitude of it? So the heat transfer requires both the idea about the temperature distribution of the body along with the magnitude of heat transfer and the direction associated with it. So driving force for the heat transfer is the temperature difference. Higher the temperature difference, larger the heat transfer. Now, some heat transfer problems in engineering requires the determination of temperature distribution throughout the medium, and the specification of temperature at a point in the medium first requires the specification of the location at that point. So this can be done using a suitable coordinate system, such as the rectangular coordinate system or a cylindrical or a spherical coordinates, depending upon the geometry involved. So if you are having a simple plane wall, if you are having a very simple plane wall, then you can use the rectangular coordinates. And if you are having a spherical type of body, in that case you need to use a spherical coordinates. Or if you are having a cylindrical body, in that case you have to use the cylindrical coordinates. So depending upon the uh, geometry involved, you can have different application of the coordinate system, either it be rectangular coordinates or cylindrical or the spherical coordinates, to determine the location of a point from which the value of the temperature has to be obtained, or the amount of the heat transfer which is taking place can be determined. So for location of a point, we can use either rectangular coordinates, that is location of a point, it can be a rectangular coordinates, that is x, y, z in 3 dimensions, or it can be a cylindrical coordinates, that is r, phi, z, where r is the radial direction, phi is the azimuthal angle, r is the azimuthal angle, and z is the z direction. Is the video stuck? Hello?
No, sir.
Oh, okay. On my screen it is stuck, so I'm asking. Yeah, tell me. Any problem?
No, sir.
Okay. So let's move to the spherical coordinates. So spherical coordinates, it can be given as r, then your phi and this theta. So phi is the azimuthal angle, theta here is the zenith angle. So azimuthal angle is the angle between reference direction on the chosen plane and the line from origin to the prediction of the point on the plane. I think you already have gone through in your mathematics courses what is cylindrical and the spherical coordinates. So at a particular time t, the temperature at this particular location x comma y comma z can be denoted as temperature as a function of the coordinates x, y, z, comma. So now if I want to write the value, all of you are able to see the PPT? Are you able to see the PPT or not? No? And for this is for the rectangular coordinates. For the angular coordinates, and for the cylindrical coordinates, I can write the temperature as a function of r, phi, z, comma t for cylindrical. In case for spherical it would be t as a function of r phi theta comma t for the spherical coordinates. So if you see the PPT now, you are all able to see the PPT, right? Yeah. So you can see for rectangular coordinates, for the cylindrical as well as for the spherical coordinates. So you have this specification. Now, coming to the conduction rate equation. So in our first class, we have studied that the basic law for the conduction is the Fourier law of heat conduction. So for a plane wall in which the heat transfer is taking place from a higher temperature T1 to a lower temperature T2 for a thickness delta x, or sorry, dx here, I can write the heat transfer taking place in positive x direction would be qx is equal to minus ka dt by dx. This is the rate of heat transfer. Okay. So I can also write this in terms of flux, that is q dot upon a, that is equal to minus k into dt by dx. Now, generally, the heat flow will be always be normal to a surface of a constant temperature. So, if you are considering for a particular direction, for example, if you are considering for y direction, so in that case, you can have it's equal to minus k dt by dy. If you are writing for only z direction, in that case, you can have a k into dt by dz. So, if I am writing for heat transfer, I can define for a normal direction, the heat flux in the normal direction is equal to minus k into t by. Now, if I am writing for the rectangular coordinates, so respectively for the x direction, I can have minus k dou t by dou x. For y direction, I can have as minus k dou t by dou y. For z direction, I will have it as minus k dou t by dou z. Now talking about the cylindrical coordinates. So cylindrical coordinates, you can write QR is equal, that would be minus k dou t by dou r. For azimuthal direction, so you can have q phi is equal to minus k into 1 by r dou t by dou phi. And for z direction here, you can have as minus k dou t by dou z. Similarly, for the spherical coordinates, you can have this as, for the radial direction, you can have it as minus k dou t by dou r. Q of theta is equal to minus k into 1 by r dou t by dou theta. Q of phi is equal to minus k into 1 by r sine theta into dou t by dou phi. So this will be the values for the heat flux in the different coordinate systems. That is, first is the rectangular, second is cylindrical, and third one is the spherical.
Excuse me, sir.
Yeah, tell me.
Could you just please shift the page a bit to the left? Uh,
Uh,
yeah.
left.
Or just zoom out because it's not fitting in our screen.
Okay. Okay. I think recording has stopped. Stopped here.
No, sir, it's been recording.
No, sir, it is recording.
It is
Sir,
recorded.
it's
Oh,
fine. Sir,
okay.
it's fine.
Yeah. Tell me. The network is not good. I'm trying to reconnect
Sir,
again and
can
again.
you zoom out
Yeah.
the sheet?
Zoom out the sheet. Are you able to see now the rectangular? Rectangular.
Yes, but not the spherical. Yes.
Now it's fine, sir.
Mm. Shall I write it again on a different page? In
No,
that
sir,
case,
it's
you can
fine.
have a clear view of it. So, okay, I will write on a different page. So, for rectangular, I had heat flux as minus K into dou T by dou X. For Y direction, I had minus K dou T by dou Y. For Z direction, I am having it as minus K dou T by dou Z. Right? Now it is clear. Clearly, you can see now, right? Now, similarly, for the cylindrical, I am having for the radial direction as minus K dou T by dou R. For the azimuthal direction, I am having minus K into 1 by R into dou T by dou phi. For the Z direction, I am having as minus uh, K dou T by dou Z. Now for spherical, I am having it as Q R, that is in the radial direction, minus K into dt by dr. For zenith angle direction, I am having it as minus K into 1 by R dou t by dou theta. And for the azimuthal direction, I am having minus K into 1 by R sine theta into dou t by. So these are the definitions of the heat flux for different coordinate systems in the different directions. Any problem up to this part?
No, sir.
Okay. So shall we move forward now? So there are classification of heat transfer problems. So the heat transfer problem either can be a steady state heat transfer problem or a transient heat transfer problem. Sorry, I should use and here. And transient heat transfer problems. So when I'm talking about the steady state, that means that implies that there is no change with respect to time. That means in that case, your t, which was varying with the axial coordinates as well as with time. So in that case, this won't be varying with respect to time now. It will be written only as a function of the coordinates, that is x, y, and z only. So if we talk about this steady state, so let us consider that there is a plane wall, a simple plane wall, okay, and this is a positive x direction. And let us consider that there is a very small element here, and considering that the heat transfer is taking place in the positive x direction from a higher temperature on the left hand side to a higher lower temperature on the right hand side, high temperature to low temperature. So the direction of the heat transfer will be from high temperature to low temperature. So let us consider that Qx is the amount of the heat transfer which is taking place. Now, if it is steady state, okay, so it will be the same amount of the heat transfer which will be transferring through this plane wall. Now, if I consider this small element of say thickness delta x or say dx, okay. So if it is not a steady state, I could write that the amount of the heat transfer which has taken place here would be q of x plus dx. If it was steady, then we would have a very similar value. But since I am not considering it to be a steady state, so I am writing as q of x plus dx. So if I am writing here q of x minus of q of x plus dx, so in that case this will be equal to minus of d by dx of qx into dx, as q of x plus dx can be written as qx plus d by dx of qx into dx. So if you put the value here, okay, so qx will be cancelled out. This will be the remaining value. So now if you write the value of Fourier's law of heat conduction for this qx here, so in that case q of x minus of q of x plus dx will be minus d by dx. Qx definition is minus k into a into dt by dx from Fourier's law of heat conduction into dx. So A is the area normal to the direction of heat transfer. So if it is a steady state, the value for this qx minus of q of x plus dx is going to be 0. If it is a steady state, this value will be equal to qx, and so it will be equal here. So the difference of these two quantities will be equal to 0. So in steady state, I can write minus of d by dx, minus sign, so it can be written as positive. So k into a dt by dx into dx is equal to 0. Now, since this is a differential here, you can also write from here that your dt by dx from here, this point, that is your dt by dx is a constant value. Dt by dx value is constant. So that indicates that if there is a steady state heat transfer, your temperature gradient is going to be constant. So when you are taking the readings, and when you talk about that whether we have reached the steady state or not, so in that case you find that the temperature readings are having a very minimal difference, maybe a 0.2 degree centigrade or maybe less than that. So that indicates that your temperature gradient is being constant and a steady state is being achieved. Now, why we need a steady state? So for a design of a heat transfer equipment, for considering that you are having some conditions for which this heat transfer equipment is being exposed. So to have an idea about the limitations or the efficiency of any heat transfer equipment in adverse conditions, we need to have an idea about the steady state heat transfer. For example, that you are having any heat transfer equipment, okay, considering that you are having a temperature in adverse conditions as minus 5 degrees centigrade, lower temperature, and some say high temperature as some 2 degrees centigrade or whatever the room is being maintained. So for that, what is the value of the heat transfer, or how the system is having or how system is operating under the adverse condition? For that, we need to have an idea about the steady state heat transfer. So basically, for the design of the heat equipments which are being exposed to adverse conditions, we need to have an idea about the steady state heat transfer. Now, transient heat transfer gives us a real picture of the heat transfer taking place in different conditions, where the temperature is varying with respect to time. That is, it is a function of the axial coordinates as well as with respect to time. So this gives a real picture to us. This transient heat transfer gives a real picture to us how the heat transfer is taking place in a body or in any heat transfer equipment. Now another type of heat transfer problem is the multi-dimensional heat transfer problem. Multi-dimensional heat transfer problem. So it can be one dimensional, or it can be a two dimensional, or it can be a three dimensional problem. So one dimensional, so temperature will be only a function of one of the coordinates, so t as a function of x. Two dimensional, that is say x comma y. If you are writing with respect to time also, so in that case it will be x comma t. If you are writing with respect to time here, it can be x comma y comma t. For three dimension, it will be x comma y comma z for a steady state. For transient heat transfer, it would be function of x, y, z as well as the time t. So in your course, we will be discussing one-dimensional heat transfer in this chapter 2 and 3. Two-dimensional in chapter number 4 we will discuss. But a real picture in generally in simulations, CFD simulations, or in experiments also, the real picture is given by the three-dimensional variation of the temperature in a body with respect to time also. Now another type of heat transfer problem which you will be seeing is the heat generation. So we have already discussed in chapter number 1 about the energy generation or the heat generation. So if there is any conversion of any source energy into thermal energy, so in that case, energy generation terms adds up in the energy balance. So a medium through which the heat is conducted may involve the conversion of electrical, nuclear energy into heat or thermal energy. So in heat transfer analysis, such conversion processes are characterized as heat generation. So for example, if there is a resistance, okay, resistance R and current is flowing through it. So in that case, I can give the amount of the heat which is coming out as I square RT. Okay, so or you can take an example of an electric iron, where there is a resistance on the which is attached to the plate. If you see in the old iron, there is a resistance plate which is being attached to the plate side. So that is also example of a heat generation. So heat generation is basically a volumetric phenomena, and it occurs throughout the body of the medium. Heat generation is a volumetric phenomenon. And it occurs throughout the body of the medium. So we define that the rate of heat generation in a medium is generally specified as per unit volume. Heat generation is defined in any body as per unit volume. So we define it as Qg, the amount of the heat generated in a medium. So if we write this per unit volume, I denote it by Qg. That is the amount of the heat generated in a body per unit volume. So Qg is, that is the volumetric generation, is will be having a unit as watt per meter cube. That is the amount of the heat generated per unit volume of the body. So it has a unit watt per meter cube. Now the rate of heat generation in a medium may vary with time as well as the position within the medium. So if I need to define the total heat generation, so total heat generation, I can define it to be as Qg equal to volumetric integral Qg into d. So this will give us the value of the total rate of heat generation in a medium. Any problem up to this part? So generally the heat generation problem, we generally you will find this heat generation problem in case of some appliances where some resistance is being attached, or in the electronic cooling systems also this heat generation problems comes up. So the safe and effective removal of this heat away from the side of the heat generation is the subject of electronics cooling also. Now we will discuss the general heat conduction equation or the heat diffusion equation. General heat conduction. So let us consider that there is a small rectangular element. Small rectangular element like this. I should have made this dotted here. So it is having the length as dx, width as dy, and height as dz. So this would be dx. Then this is your dy. And say this is your dz. This is a rectangular element. Okay. And the respective x, y, and z directions are x, y, and z. Now, if you are saying that this is a rectangular element and the heat transfer is taking place here from a high temperature side to low temperature side. So considering that the heat transfer in x direction here as qx, q of x plus dx. For y direction, it would be qy, q of y plus dy. For z direction, it would be qz, q of z plus dz. Okay. Now let us assume that the density of this rectangular body is rho and the specific heat capacity is Cp. Now if we consider a heat generation per unit volume in this rectangular element as Qg, so the amount of the heat generation would be this Qg value multiplied by the volume of the element. So Qg into dx into dy into dz would be the total heat generation within the body here. So let's apply the energy balance on this element during a very small time interval, that is your dt. For a given small interval, I can write the energy balance as rate of heat conduction at x, y, and z minus rate of heat conduction at x plus dx, y plus dy, and z plus dz plus rate of the heat generation inside this element can give us the rate of change of the energy content of the element. According to the first law of thermodynamics, that is energy balance, which we have discussed in chapter number 1, I can write that is E in minus E out plus energy generated is equal to change in the energy of the system. Change in the energy of the system. So I can write for energy in, I can write it as Qx plus Qy plus Qz minus E out. E out would be Q of x plus dx plus Q of y plus dy plus Q of z plus dz. So this will be E in, this is your E out. Now plus energy generated, that is Qg into dx, dy, and dz is equal to change in the energy of the system. Now we can write the value for q of x plus dx So I can write from here it to be u of x plus dx as qx plus dou by dou x of qx into the element length, that is dy as equal to qy plus dou by dou y of q dot y into dy. Similarly, for q of z plus dz, I can write it to be q dot z plus dou by dou z q dot of z into dz. Now, if I put these values into this equation here, so qx, qy, and qz will be cancelled out. So from here, I can have minus of dou by dou x of qx into dx then it would be minus dou by dou y of q dot y into dy minus dou by dou z of qz into dz plus the heat generation term, that is qg dx into dy into dz is equal to change in the energy of the element or the system here. So,
Sir, we can't see her.
uh, so what I was saying that if you put the values of q of x plus dx, q of y plus dy, and q of z plus dz into the equation above here, which we have written for the energy balance here. So if you put these values, so qx, qy, and qz will be cancelled out in this equation. So the remaining term here would be left out as minus dou by dou x of qx into dx, minus dou by dou y of qy into dy, minus dou by dou z for qz into dz, plus the heat generation term which we are having in this equation. Up to this point, any problem? Any problem up to this part? No. Okay. So let us write for the RHS side, that is the change in the energy content of the system. So if you recall, the energy change in the system when there is a heat transfer is going on, we write it as mCp dt. So for m, if I am writing, I can write the mass as the product of the density and the volume. So density is rho. What would be the volume for this element? It would be dx into dy into dz. So you can write dx into dy into dz. So this is giving you the mass. Now multiplying it with Cp, mCp. Okay. And writing the temperature, that is dt. So I can write it dou T by. So here capital T is for the temperature, small t is for the time here. So this is a time derivative of the temperature. This is mCp dt, energy content of the energy change of the system. Okay. Now using the Fourier's basic law, I can write the expression for qx, similarly the expression for qy, and similarly the expression for qz. So writing the expression for qx, qy, and qz from Fourier's law of heat conduction, so qx will be equal to minus k into area normal. So if you see for the x direction, what would be the area normal? It would be product of dy and dz. Area normal. So this is the direction of heat transfer. So area normal to the direction of heat transfer would be dy into dz. So writing that area normal, that could be dy into dz, k into a into dt dou t by x for the x direction. Similarly, if I am writing for the y direction, I can write q dot of y is equal to minus k area normal in y direction. So in y direction, what would be our area normal here? That would be the dz into dx. So the area normal here, I would write dz into dx into dou t by dou y. Similarly for z direction, qz is equal to minus k. Area normal would be dx into dy into dou t by dou z. Now let us put this qx, qy and qz in this equation. Qx, qy and qz. So you can write from here as minus dou by dou x minus of k dy into dz into dou t by dou x into dx minus dou by dou y into minus of k into dz into dx into dou t by dou y minus dou by dou z minus k into dx into dy
So there
into
will
dou.
be dou y also.
Yeah, anyone is having any problem?
So there will be a dou y and dou z
Can
also.
you speak a little bit loudly? I'm not able to hear.
So you have missed dot dou y and dot dou z in the last term
Second term, sir, in the last equation.
and also the third term.
Second equation, here you are saying,
Yes, sir. And the third term also.
so is
Dot
there any mistake you are saying?
dot dou y, sir. Dot dou y and dot dou z.
Sir, in the second term, you have not multiplied with dy.
Yeah, okay, okay. dy here and dz
And
here.
dz here. Yes, sir.
Any other problem? It is okay, right?
Yes, sir. Now it's fine.
Okay. So plus heat generation term, that would be qg into dx into dy into dz is equal to the energy change, that is rho into dx into dy into dz into cp into dou t by dou t. Now if you see this equation, you can see dx into dy into dz in all these parts are common. Same on the LHS side, same on the RHS side also. So you can just cancel it out. So let us move forward to the next equation. If I cancel, take common dx, dy and dz and cancel it out, then the remaining equation would be dou by dou x into k into dou t by dou x plus dou by dou y k into dou t by dou y plus dou by dou z k into dou t by dou z plus the heat generation term, that is qg, is equal to rho into cp into dou t by dou t. Since we are cancelled out this dx, dy, dz, which is common in all these terms on the LHS as well as on the RHS side. So we are having this equation now. Now from here you can have this k into dou squared t upon dou x square, taking k as common here, so plus dou squared t upon dou y square plus dou squared t upon dou z square plus qg is equal to rho cp to t by. Or you can divide this equation by k. So in that case, this equation will turn to dou squared t upon dou x square, dou squared t upon dou y square, squared t upon dou z square plus qg upon k is equal to rho cp upon k into dou t by. This equation is known as the general heat conduction equation. Now this ratio, that is K is the thermal conductivity, rho Cp, this is indicating the heat storage capacity. So the ratio of the thermal conductivity to that of this heat storage capacity is termed to be as the thermal diffusivity. So you can write this equation now here. Equation by equal to 1 by alpha into T by T, where alpha is the thermal diffusivity. And it is equal to K upon rho Cp. K upon rho Cp. So thermal diffusivity, it has significance that it indicates the material's ability, that how much faster the heat diffuses into the system, or the ability of the material to diffuse the heat into it. So it is indicating the ratio of the thermal conductivity, that is the material's ability to conduct heat, to that the material's ability which it can store the heat. So ratio is indicated by the thermal diffusivity. So this is termed to be as the general heat conduction equation. So any heat conduction problem, you can apply this equation, whether it is a steady state heat transfer or a transient one, you can apply this general heat conduction equation. So at this point, I am stopping your class, since you are having a class at 10 also. So in the next class, we will discuss various conditions when there is a no heat generation, a steady state, or a steady state one dimension, and in that case also no heat generation. For that, what would be the form of this equation which can be applied to certain problems.